Okay, hey folks, so this is actually going to be the last video for this week on Chapter 7. So we're doing 2 full weeks of Chapter 7. This is going to be the last one, so I'll do an air horn for that. All right. So in this last video for this week, which will also get you enough to do the Part 1 assignment, okay, we're going to talk about the Bohr model of a hydrogen atom and how that leads to an emission spectrum. And from that, we're going to learn how to do calculations using the Radberg equation, which I also want you to be able to do. And from these first 6 learning goals, that's going to allow you to complete the Part 1 assignment, which I would fully encourage you to do. Even though it's not due until 2 weeks, I would focus and dig deep and do it. Okay. So let's talk about spectroscopy. I'm gonna go back to my black pen here. Okay. Spectroscopy. Okay. And specifically, this is called emission spectroscopy due to the emission of light of a material. So suppose we have a hydrogen lamp. So believe it or not, we can have a hydrogen lamp. Many of you are familiar with neon lamps. And yes, those are filled with the gas neon. It's not some like trademarked or whatever. A neon light literally has neon in it. So just the same, we can have a hydrogen light as well. And if we pump a bunch of energy into one of these types of lights, these are called gas discharge tubes, then it will glow. And it will glow a characteristic fingerprint, okay, that we call its emission spectrum. So each atom, each molecule has its own unique fingerprint of an emission spectrum, and that's how we can identify what is in certain materials. So for example, now if we had this glowing gas discharge tube, it would kind of have this pink color, and our eyes are pretty crappy light detectors, so we couldn't tell exactly what colors were coming out of this. It would just look like this overall pink color is kind of there. But now if we were to put this in a prism, which I talked about this, right? In this prism, because there's different densities, so the light wavelengths travel at different speeds, those wavelengths will become separated, just like in the Pink Floyd Dark Side of the Moon picture, right? Let's back up to that. Right, this picture right here, so the refraction, okay? And so, of course, this is showing if you have white light, you'll get all the wavelengths, but instead, rather, if you have light coming from a specific atom or molecule, it will only have those characteristic fingerprint wavelengths of that atom or molecule itself. Okay? And for hydrogen, we would see 4 lines in the visible, 410.1, 434.1, 486.1, and 656.3. So all of these together combined to us would look kind of pink because we don't have prisms in our eyes the same way that this does, right? Our eyes can't separate those wavelengths. But a fancy electronic device like a spectrometer could. And thus we would get the fingerprint of that material, okay? So here's what some other fingerprints look like. So again, here's hydrogen. And so as we get to more complicated, bigger atoms, they have more complicated fingerprints. So helium, even though it's just 1 extra electron, right? We recognize hydrogen as 1 electron and 1 proton. Well, helium has got 2 electrons and 1 proton and 1 neutron, okay? So it gets a little bit more complicated. And you can see that right here. It's got more lines. And in fact, this is actually a helium lamp. Someone very creatively made these glass-blown tubes, filled them with these elements, and then discharged them with a high power source so that you can see what it looks like, but then a spectrometer shows you all of those wavelengths. And then now right here's our famous neon lamp. And there's a reason why neon lamps always look kind of red, because you can see the majority of those characteristic fingerprint lines are red. And in fact, you can make some yellow and some green neon lights if you filtered out those red wavelengths. But notice how there's nothing that's blue. So if you've ever seen a blue neon light, it's not neon. It's something else. Neon does not emit any blue light. So it could be a helium light or another atom that emits blue light. But no such thing as a blue neon light. So now you know. Okay, so moving on. So this is how I'm going to start to build this whole idea up of how we get these specific fingerprint wavelengths, okay? And so this idea is kind of based on the Bohr model. And so this idea, I'm going to skip ahead, and what I'll show you with the Bohr model, the idea behind the Bohr model is, here is the nucleus in the center, okay? So that is our protons and neutrons, okay? And in the Bohr model, electrons exist in these orbits. So I'm going to call these electron orbits, okay? And these orbits are given by what we call N, principal quantum number, okay? So I know we use N for number of moles, but we also use it to describe what's called the principal quantum number, which gives us these, that says electric orbits, electron orbits about the nucleus, okay? So for example, the N equals 1 is the closest orbit to the nucleus, okay? So we call that the ground state. N equals 1 is the ground state. That's where we expect electrons to exist at room temperature. Under normal conditions, electrons will be in this ground state, okay? So now look, we've got this N is equal to 2 level right here. Or N is equal to 3 or 4 or 5 or 6, 7, 8, 9, 10. They're whole number integers, okay? Those are what we call excited states, all right? And so what happens in these excited states is we typically pump energy in. So that's done by that gas discharge, right? So I talked about how, so really, let's see, if I finish drawing this thing, I'm just going to draw this as like a closed circuit, okay? So we're pumping electrons, we're pumping, energy through this thing. We're giving it power. So maybe there's a battery hooked up or it's plugged into the wall or something like that, okay? So energy goes in, and I'll draw that with these arrows. And as it turns out, when energy goes in, it pumps these electrons up to these various excited states. This is part of what we call, this is why we call it quantum mechanics, because quantum, what that really is referring to is that these energies are quantized. So in other words, when these atoms absorb energy, they only absorb specific quantities of energy. They absorb, so I'll say energy in right here. They absorb exactly the energy they need to go up to these various levels. So everything starts at the ground state, but perhaps they might, if there's enough energy to take it all the way up to level 5, that would be a lot of energy. So on this scale, the longer the arrow, the more energy is being absorbed. So it could absorb up to level 4, up to level 3, up to level 2. So we're pumping a bunch of energy, enough energy to populate all of the excited states. So we're pumping electrons into these excited states, putting them into higher energy orbits, okay? And so now these molecules or these atoms, they don't like being in these high energy states, so they relax. And they relax by releasing energy, and that energy is quantized. Okay, so I'm going to draw a purple line right there going from 5 to 2. And now I'm going to draw like a little, let's see, do I have a cyan color? I'll use blue. So I'll draw a blue color going from 4 to 2. Oops. So a blue color going from 4 to 2. And then now I will draw a red color going from 3 to 2. And I'm going to draw, let's see, what color haven't I used? I need a different purple color, so I'm just going to use another black, and I'm going to make it dotted. And then, oops, and I'll explain why I chose specifically all of those colors. Let's go with like a gray, okay? And I'm just going to show that one going all the way down, okay? So there become all of these different combinations of energy relaxation. So that's now energy out. Okay, I don't know why I drew a box right there, so we'll have to deal with that. So all of those arrows refer to energy out. Well, hopefully you can see where this is going, okay? Because as it turns out, this line here at 434 is related from going from level 5 to level 2. And this is specific for hydrogen. So other atoms will have different spacings in their energy levels and thus give you a different fingerprint. Okay. So going from 4 to 2 gives you this 486 line, this kind of cyan blue line. Okay. And going from 3 to 2 gives you this red line. Okay. And so I'll remind you that this is the biggest energy, so I'll write high energy up here and low energy up here. And you can see that's why 3 to 2, from level 3 to level 2, only gives you a red light because red is lower in energy than blue. So that 4 to 2, that's a bigger arrow, that's a bigger energy gap, so that requires more energy. Okay? So now what about level 2 to 1? Well, as it turns out, level 2 to 1 is ultraviolet. So that's such a big gap. And remember, the size of the arrow on this diagram indicates how much energy there is. So as it turns out, level 2 to level 1 has the biggest gap, and that's true for all things. So it actually gives you ultraviolet in the case of hydrogen. But now, once again, this 3 to 2 gives you that red line, this 4 to 2 gives you that blue line, and this 5 to 2 gives you that purple line, okay? And so that's kind of being showed to you here on this Bohr model with all of these indicated lines, right? From 5 to 2, from 4 to 2, and from 3 to 2. And certainly from 2 to 1 exists, that happens, but we wouldn't be able to see that visibly with our eyes because it's ultraviolet, okay? So now this is the equation that we use here. So this is our Radberg equation, and that says delta En, and what that means is the difference in energy level, because as it turns out, it is the difference, the delta, right? So we recognize delta En is going to be En final minus En initial. The difference between those two energy levels is what gives us light. It's what gives us that characteristic fingerprint, okay? So let's do an example, okay? How much energy is required to excite hydrogen from its ground state to the N is equal to 3 level? What wavelength of light is required to make this transition in units of nanometers? So basically what we're doing is, suppose we wanted to use light not to populate all of the energy levels like I showed you in this diagram. So in one of these emission tubes, you're just putting a crap ton of energy in there, so it gives you all of the wavelengths, or it gives you all of the fingerprints from those various transitions. However, what this question is asking you, suppose I want to very specifically only use enough energy to go from level 1 to level 3. We can also do that, okay? So how much energy is required? So that's going to be our Radberg equation. And this is how that equation is going to go. It says, man, this is bugging me that I got this box right here. Can I erase that box? No. What are you doing? Oh, brother. Jeez Louise. Okay, that's fine. We'll deal with it. Okay, so delta En, so that equals negative 2.178 times 10 to the minus 18 joules. That's the Radberg constant. And it's times this thing over here, z squared over n squared. And then when we make this delta, it becomes z squared over delta n squared. So z squared is nuclear charge. And for hydrogen, z equals 1. It's got 1 proton, so z equals 1. So for hydrogen, what this ends up becoming is now, I'll just say, it becomes 1 over delta n squared. And the way that I do that, the way that's going to work is, that means it becomes 1 over n final squared minus 1 over n initial squared. So once you establish that's how you do it, then this calculation is actually pretty straightforward. Okay? And there is a negative sign in that equation, and I'll show you what that means in a second. Okay? So negative 2.178 times 10 minus 18 joules times 1 over n final squared minus 1 over n initial squared. So because it's asking us to excite, the ground state is my initial, and the excited state is my final. If this were asking us what color of light is emitted, then it would be the opposite. We'd be starting at level 3 and going down to level 1. Okay? So now that's 1 over n final, and it's just simply 1 over 3 squared. It's literally just that value of n, 3, 1 over 3 squared minus 1 over 1 squared. As simple as that. Okay? And so now, that gives us negative 2.178 by 10 minus 18 joules. And that's going to be it's going to be times 1 over 9 minus 1. Okay? So first what I'm going to do is just say 1 divided by 9 equals, and then minus 1 equals. And so now that gives me negative 2.178 times 10 to the minus 18 joules times negative 0.888 repeating. And I'm just going to leave that in the calculator. And now I'm going to say times 2.178 E18 negative. And then I forgot to put the negative sign on my calculator, but I recognize a negative times a negative is going to give me a positive. So that's positive 1.936. And I can use 4 sig figs here because I have 4 sig figs from the Radberg. So times 10 minus 18 joules. So now what's the significance of the sign? Well, the fact that this had a positive sign tells me I have to put energy in, which makes sense because that's exactly what I'm showing on my diagram. Positive energy goes in. If it were the other way, right, if I had flipped this, so if it was going from level 3 to level 1, I would get the same value, but it would be negative, and that negative tells me that energy is going out. So it's just like in thermo, okay? So now the second part is what wavelength of light is required to make this transition. Well, now what I can do, I remember that E always equals hc over lambda, okay? So I have a value for energy, even though this was delta En, I can still say all of that equals hc over lambda. So now to solve for the wavelength, I'm just going to do some algebra, because that's what it asked me for, what wavelength. So wavelength equals hc, now divided by E, so I just did some algebra. And we'll say that lambda is 6.626 times 10 minus 34 joules times seconds times 2.998 times 10 to the 8 meters per second, all divided by 1.936 times 10 to the minus 18 joules. And so let's do that. So on this one, I'm going to say times 1 negative to make that a positive. So we always use positive values. So like, I'll put an absolute value sign around that energy. Because if I was doing this from 3 to 1, I would still get the same number, but it would be negative. I would just use the absolute value of that in my equation, okay? And so now I've got that in the calculator. I'm going to show you a handy trick what I can do. Because it's 1 over this number, right, 1 over the number I have in my calculator, I'm going to push that 1 over x button. Okay, great. And now I'm going to say that number times 6.626 E34 negative equals, and then now times 2.998 e to the 8 equals, and that, yep, that's a reasonable number. And I'll tell you why I know that's a reasonable number. 1.026 times 10 to the minus 7. And once again, let's do the units. Joules and joules cancel. Seconds and seconds cancel. So that's meters. And I know in 1 meter, there's 1 times 10 to the positive 9 nanometers. So minus 7 and positive 9 gives me positive 2. So that equals 1.026 times 10 to the 2 nanometers, which is the same as 102.6 nanometers, and that's ultraviolet. And that makes good sense that it's ultraviolet light, because if I back up here for a second, right, so all of these smaller levels, so the levels that are crunched together are all giving me visible, right? So like 3 to 2 gave me red, and 4 to 2 gave me blue, and 5 to 2 gave me ultraviolet. So then it makes sense that 1 to 3 would also be ultraviolet, because that's a fairly large arrow in comparison to, let's say, the 3 to 2 or any of these other arrows, okay? So once again, the spacing between these energy levels, the higher they're spaced, the more energetic it is. And the more energetic it is, the more likely it's, ultraviolet or X-ray or something like that, okay? Okay, so we're going to do more of these types of calculations and discussion. So now moving on, so the last thing that I want to talk about is adjusting the Bohr model. Because as it turns out, the Bohr model works really well for hydrogen. But that's it. If you try to apply the Bohr model to anything else, helium, lithium, sodium, etc., it fails. And the reason why it fails is because hydrogen only has one single electron. And this is where this is going to get crazy. This is where there's like a mind explosion. So we talked about interference with light, okay? So we talked about how, like, if I have two interfering waves, right? Let's say if they destructively interfere like so, and I add these together, then I've got nothing, right? Or if I add them together constructively, then it results in an even brighter spot. Well, this is where this gets crazy. Electrons in atoms also have wave-particle duality. Sorry, that's getting sloppy. So, once again, electrons in atoms, and this is the crazy part of quantum mechanics. As soon as you remove an electron from an atom and send it off into vacuum, it behaves like a particle. So a free electron, so we'll say that again, free electron is like a particle. But a bound electron acts like a wave. That's crazy. So light isn't the only thing that's suspect to wave-particle duality. So, and what I mean by bound electron is an electron that's in an atom, an electron that is bound to a nucleus through those electrostatic negative-positive charges. Okay. So now the reason why the Bohr model works for hydrogen is because there's only one single electron. There's nothing for that electron to interfere with. However, if let's say we put 2 electrons in here, so I'm going to populate, let's say, this level with 2 electrons, okay? Well, as soon as I put 2 electrons in that same orbit, they actually start interfering with each other. They can interfere with each other constructively, or they can interfere with each other destructively. All right? And that makes the Bohr model just not work. We can come up with other models that get quite complicated, and that's largely what quantum mechanics is all about, is trying to calculate these types of properties for more complicated molecules. However, the gist of it, to adjust the Bohr model, now instead of having these orbits, like these planetary orbits, these orbits actually have a wave pattern, right? And so you can see here n is equal to 1. It's really hard to tell, but n is equal to 1 would only have one oscillating period, okay? N is equal to 2 would have 2 oscillating periods. N is equal to 3, this one's easier to see. N is equal to 3 would have 3 oscillating periods. I don't even know if I could draw n is equal to 4, but you get the idea. These orbits are no longer like these planetary orbits, but they themselves are also like waves. And the waves of these orbits are given to us by the de Broglie wavelength equation. Okay? And in the de Broglie wavelength equation, we still have Planck's constant h. Okay? But now this becomes mass of the object in question, and this becomes the velocity of the object in question. Now, in this discussion, we've been talking about electrons. And if we were to use the de Broglie wavelength equation, we would use the mass of an electron, and we'd have to know what its velocity is. And that would actually give us the apparent wavelength, so the distance, you know, from peak to peak, or the distance from trough to trough, right? That would give us the apparent wavelength of an electron. However, de Broglie, he was a really smart quantum mechanicist, a very young one at that too, when he came up with this, very young man. He said, well, electrons, because they have mass, if those are suspect to wave-particle duality, then so too must everything else that has mass. So a human, a proton, a tree, a car, whatever. If an electron can have wave-particle duality, so too can everything else. And this is like, this gets into big picture stuff, and it actually starts to get into general and special relativity, when now we start talking about if I accelerate an object to close to the speed of light, so like a human or a tree or a car or something, right? If I accelerate myself at or near the speed of light, you would start observing my wave properties. So I largely exist as a particle right now, right? Like I can, just like a particle can collide with stuff and bounce off something, like my head is like a giant particle colliding with a metal pole. I definitely bounced off that. I did not interfere with it and like pass right through it, okay? Like an X-ray can pass right through your body. But according to all of this, and this is yet to be proven, but according to all of this, if I can accelerate myself to at or near the speed of light, so that would be the velocity approaching the speed of light, then I would start to have wave properties. I could interfere with something. I could maybe even pass right through something if my wavelength was sufficiently small enough, okay? And this is what's created the basis in science fiction shows for, you know, beam me up, Scotty, right? That's the whole idea, is that if you could turn a human into a wave, then you could make that happen, okay? And so here's one final picture of this whole idea of these wave-like orbits. So this is hard to imagine this, but if you look at this here, this n is equal to 3, and this is called stable, and what that means is when I'm following this wave, let's see if I can draw it, there's just a continuation. So round and round it goes. You don't know where it stops. You don't know where it finishes. So I get 3 complete waves round and round, okay? And so that means these numbers, these principal quantum numbers n, they have to be whole numbers. Because now, right, if I make it 2 1/4 or whatever, it's not going to start and stop at the same place. Another really good example, for you guitar players or string instrument players, you actually can observe this all the time when you like pluck a string. So let's say you're plucking the strings right here, and the bridge is located right here. Well, this becomes some length, okay? And so now if you get exactly 1/2 wave occurring over this, that would be the principal quantum number. So that would be the principal tone of the instrument, okay? And if you started chopping this in half, and the way that I could chop that in half, think about this, string instrument players. I would put my finger, so let's, right? If I put my finger at exactly that fret, I would have found the first harmonic of the instrument. Maybe you know that term. On guitar, that sounds like that really high-pitched bing. When you make that sound, bing. When you do it exactly half of the length of the guitar, that's the first harmonic. If you were to do it 1/4 of the length, it would be the second harmonic. If you do it 1/8, it would be the third harmonic. This also creates the basis of octaves in music when you split these waves up based on whole integer number wavelengths. So there's some pretty cool stuff that's going on here. But the important thing to note is you can't have these integer numbers. It's got to be these whole number wavelengths. Okay, folks? So this stuff is pretty tough to grapple. It's out there. It's very abstract. We have very little things in our common everyday experiences that allows us to kind of think about this stuff other than like music and instruments. So it's pretty weird stuff. So if you're left thinking, whoa, that's weird, it is. It's very cool though. So I would encourage you to find some like Nova channel or BBC or Discovery Channel stuff on quantum mechanics, and particularly on de Broglie wavelength and wave-particle duality. There's some really out there wacky stuff that's physically correct, but it's just wacky. It's different and bizarre. It defies your everyday experiences. Okay, folks, so that's all I'll say now. So just these 3 videos for this week. Next week, it'll be maybe 3, possibly 4 more videos. So this should be enough to get you through the first part of homework, part 1. So that's a 20-pointer. So after you finish all 3 of these videos, do yourself a favor, do me a favor, just finish that part 1 homework. All right, folks. Later, hosen.